Hey y'all, today I'm going to lay down the law, Coulomb's law. We're going to talk about what it means. We're going to talk about exactly how we're going to use it in this unit, and I'm going to kind of foreshadow the fact that we're going to be using this all year long. But in order to use it, we need to understand it. And in order to understand it, I'm going to teach it to you today. So let's go ahead and get started with Coulomb's law. All right, let's start with a quick recap of what you know so far. At this point, we've talked about the model of an atom, the quantum model. We've talked about how to build an atom using electron configurations. We understand isotopes. In other words, how atoms of the same element differ based off of their numbers of neutrons. We've talked about ions, which is how atoms differ based on their numbers of electrons. Now we're going to apply a lot of those principles to the actual physics of chemistry. In the end, Coulomb's law comes down to understanding that two charged particles, are going to either attract each other or repel each other based off of their relative charges. If you have two positive charges, they are going to repel each other. If you have two negative charges, they're going to repel each other. However, if you have a positive charge and a negative charge, they will attract. The other thing we talked about is how different electrons within an atom are in different energy levels or shells. And those different energy levels are at different distances away from the nucleus, with the valence electrons being the furthest from the nucleus and core electrons being closer to the nucleus. All of that's going to play in this video. Coulomb's law allows us to actually calculate the force of that attraction or the force of that repulsion. So, what do we need to know to be able to calculate this? The first new thing you need to know is something called effective nuclear charge. Now, the effective nuclear charge is essentially how much force does a nucleus have on those valence electrons? What is the relative charge of the nucleus? Now, the nuclear charge of an atom is simply how many protons it has. The effective nuclear charge, you take that number and you subtract the number of core electrons from it. So if you have, let's say, 6 protons and 2 core electrons, your effective nuclear charge would be +4. If you had 11 protons, and let's say you had 10 core electrons, your effective nuclear charge would instead be +1. Effective nuclear charge is sometimes referred to as Z effective, and sometimes you'll see that utilized in Coulomb's law, where it's Z effective, big Z, little effective, all right, is equal to the effective nuclear charge. The next variable we're going to look at with Coulomb's law today is going to be what number of electron shells or energy levels that each atom has. If an atom's in the 5th period, it has 5 energy levels or shells. If it's in the 2nd period, it has 2 energy levels or shells. So now we have 2 variables. We have the effective nuclear charge and we have the number of energy levels. Throughout the year, we're going to use Coulomb's law in a different way. But in the end, it's always the same fundamental equation. So let's talk about that equation briefly. So this equation that you see here is not actually the Coulomb's law that you're going to be using. This equation is more complicated than what we need. However, it's critical to understand where those variables we just talked about fit into this. First of all, Coulomb's law is going to calculate the force of attraction or repulsion. And in our case, we're almost always looking at attractive forces. So the force of attraction between 2 charged particles is going to equal the charge of those particles, this is Q1 and Q2, divided by the distance between those particles. That's the D. You do not need to worry about that K value. That K value is a variable based off of the properties of those particles. You don't need to worry about that. We are going to focus on the second half of this equation only. So let's replace those variables with the ones that we've talked about already. In the case of an individual atom, Coulomb's law applies to the attraction between the positively charged nucleus and the valence electrons. That's what we care about. The charge of those is going to be relative to the effective nuclear charge of your atom, Z effective. So we are doing this all non-quantitatively. We're not ever going to calculate a number for Coulomb's law. We're just doing this relative to each other. So if I have two things that have different effective nuclear charges, but the same number of energy levels, I can compare them based on their relative force. Or maybe they have the same effective nuclear charge, but different number of energy levels. Now I can compare them. You will almost never be asked to compare Coulomb's law to things that are going to have two variables. But if you do, I'm going to show you how to handle it. So here's our equation, the one that we're going to be using throughout the year. And again, we're going to apply this in a few different ways. It's not like we're just using Coulomb's law to determine the variables associated with an atom or the properties associated with an atom. We're going to be using this again in thermochemistry. We're going to be using this again in gas laws. We're going to be using this again when we talk about unit of intermolecular forces and how atoms are built or how molecules are built. We're going to be talking about it again in electrochemistry. Coulomb's law comes up time and time and time again. Sometimes the variables will be the same. Effective nuclear charge over distance. And sometimes they won't be. Sometimes those variables are going to change a little bit, but we're going to continue to use these same principles throughout the year. So it's important to have a fundamental understanding of how Coulomb's law operates, which we're going to talk about today. So applying this quantitatively, and remember, we're never going to get a real value. This is all relative values. Let's take a look at something very simple. Let's say that an atom has an effective nuclear charge of +1 and has one energy level. This would be hydrogen. The relative force of attraction by the nucleus on the valence electron would be effectively 1 over 1. And again, this is not a true number. This is not like there's one unit. All right? This is relative. But let's say we're looking at helium. Now, helium has 2 protons. Its effective nuclear charge is +2. It still only has one energy level. So what does that do? Well, we change that numerator from a 1 to a 2. Effective nuclear charge went from +1 to +2. Energy level stayed the same. So what would that tell me? It tells me that helium has a greater force of attraction on its valence electron by its nucleus than hydrogen does. That's what Coulomb's law is telling me here. It's telling me that the force of attraction on valence electrons in helium is greater than that of hydrogen. It doesn't tell me it's double. It just tells me it's greater. So if you look at the bottom corner here, you're going to see 4 different circumstances, 4 different situations. In these 4 different situations, we have kept the distance, that's the denominator, constant. But in each one of these, we have changed the variable of charge. And you can see, as the charge changes, the relative force changes too. As you increase the effective nuclear charge of an atom, the relative force of attraction on those electrons, those charged negative particles on the outside, increases along with it. What about changing the other variable, distance? This is the denominator in Coulomb's law. So now let's take our similar example where we had hydrogen, effective nuclear charge of 1 energy level. And instead of changing the numerator, we're going to change the denominator. Let's go down 1 period to lithium. Lithium has an effective nuclear charge of +1, 3 protons minus 2 core electrons. And it has 2 shells or energy levels. Now, here's the thing. What we have now done is, relatively speaking, change the denominator from a 1 to a 2. So if hydrogen's relative force of attraction on its valence electron is 1, lithium's would be less than that because 1/2 is less than 1. Now, just to be clear, this does not mean that lithium's force of attraction on its valence electrons is half that of hydrogen's. It is not half, but it is less, and we can see that it is less. So remember, Coulomb's law is not ever ever going to be used to calculate a number in this class. But we can use it to give a relative understanding of force of attraction by the nucleus on the valence electrons of each atom relative to each other. So let's take a minute to look at the model that you see at the bottom of the screen here. In this case, we have kept the relative charge constant, and we've only varied the distance. So as the distance gets longer, take a look at that force. What happens? It gets weaker. Okay, the force gets weaker as the distance gets further. So again, this is how Coulomb's law operates in this context. We are going to be applying Coulomb's law throughout the year in different ways, but it's always relative charge over relative distance. Now, Coulomb's law is an electrostatic force. Electrostatic force, that's a field force. A field force like gravity or magnetism. The relative strength of a magnet matters, but so does the distance between them. If I hold two magnets far apart, they might not be all that attracted to each other, relatively speaking, but if I hold them close together, now they are. So for example, I have two magnets here. Right now, I do not feel their force of attraction, but as they get closer and closer and closer and closer, all of a sudden I start to feel it. They start to pull towards each other, okay? And so the idea here is that these magnets are attracting are based off of their relative strengths. Okay, what happens if I strengthen my magnet? Okay, what happens if all of a sudden my magnets are stronger? Now all of a sudden, what I had with one magnet, now I've essentially tripled my magnetic strength. As I get closer and closer and closer together, these magnets are going to attract stronger and stronger and stronger. So now I start to feel that attraction at a further distance than I did earlier. A field force, such as gravity, a field force, such as magnetism. Now, Coulomb's law is not the same as gravity, and it is not the same as magnetism, but I just wanted to give you something tangible to kind of hold on to give you a better understanding of how it operates. So that wraps up today's video. Let's recap it. Today, we talked about Coulomb's law, and you are going to be so sick of hearing the words Coulomb's law by the end of this year, but it is really important to understand because it does come back time and time and time again. So the big takeaways, today we applied Coulomb's law with a single atom, looking at the force of attraction between its nucleus and valence electrons. We did this by calculating the effective nuclear charge of that nucleus, and we looked at the number of energy levels or shells of the valence electrons. In other words, the more the effective nuclear charge, the more protons are going to affect those electrons on the valence shell, and the more energy levels, the less those electrons are going to be affected by the nucleus. Because with Coulomb's law, it's charge over distance. As you increase the effective nuclear charge, you increase that numerator, you increase the relative force of attraction. As you increase those energy levels, you're increasing the denominator, which is going to decrease the relative force of attraction. I'd like to thank Sophia DeAngelis for writing, filming, editing, and producing this video. I'd like to thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one. That's going to be one of those that are probably talked about in the future. I am certain that is true. Okay. I feel like Shakespeare is... First, we're going to talk about the principle of... I felt like it was a really clean take, but people are going to hate me. Shakespeare's like the Rolling Stones. I'm just like... Effective nuclear charge is essentially how much charge does the nucleus effectively have. Now, that's a really way... Like, Shakespeare had an impact on everything. The Rolling Stones, too, right? Like the Beatles, the Rolling Stones, British Invasion. Major impacts on everything. There were better things. Is the remembering of? It's like a memorial service. Okay. Today we remember. We're free to go. I didn't say that. There are better writers. There are better playwrights. He just was groundbreaking, right? And like did things that no one else did in the way he did it. But he kind of just wrote the same type of stories all the time. An electron or an atom in the fifth period, for example, might have, or might have. And he hasn't changed in 500 plus years because he's dead. So it's not just cool science. I don't know. That was weird. I felt weirdly inspired to do something odd.